These are notes for Calculus section 2.3. The topic is continuity. Page 1. What does it mean for something to be continuous? And the something I want to talk about is specifically graphs. What does it mean for a graph to be continuous? So if we just think of a graph as a smooth curve like that, that's a continuous graph. What we want to see in a continuous graph would be no breaks, no gaps, no holes, no vertical asymptotes. Okay, so a break, think about a piecewise function. We've seen them that would have a break in it like that. That would not be continuous there. A hole in a function is a place where it's not continuous. Vertical asymptotes would be a place where also a graph is not continuous. Those are informal definitions. Let's think about the formal definition of this. A function is continuous at a number c, so that's a value for x. If this is true, if the function value at c, so the y value at c, is actually equal to the limit as x approaches c of the function. Okay, so if you think about the function sitting here, here's c. Basically what this is saying is the function value at c, which is the y value there, is equal to the limit as x approaches c of the function. And since there's no superscript there, of course, that means from both sides. Okay, so if the limit of the function is equal to this y value, and the function value is also that y value, then it's a continuous function. That is the formal definition. I want to separate that for a minute because I want to just talk quickly about continuity at endpoints. You can have a part of a function or a graph that is continuous at an endpoint. So I want to just talk about this real quick. If we have continuous at a right endpoint, I'll show you what that looks like. Continuous at a right endpoint. So let's say that we had a graph and the value c is here. Let's say this graph came up and it was defined at c. Let's say it looked like that the rest of the way. This is continuous at this right closed endpoint. Okay, because the limit as x approaches c from the left-hand side is equal to the same function value as f of c. So it's continuous at the right endpoint here. Doesn't involve this, just involves this side. Continuous at the left endpoint is a similar concept. So that's going to be where, let's say the graph was like this instead, where the open circle was here. So this is continuous at the left endpoint involving this part of the graph, because at the left endpoint, the function value f of c, it's defined here, and that's also equal to the limit as x approaches c from the right-hand side of the function. Okay, that gives you a little bit of background. Let's go into some more detail on types of what are called discontinuities. Okay, where we do not have continuity. When does that occur, and what types do we have? So we have this table we're going to fill out here. There's two basic types of discontinuities. A removable discontinuity and a non-removable discontinuity. Non-removable are also called essential. So we're going to look at where these occur. So first, I'm going to break this in half here, and we'll talk about the removables first. One type of removable continuity, simplest thing to think about, is just a hole. And I'm going to go ahead and put an axis here. We'll say at point C, we have a hole there. Where does this occur? Where does the definition break down? F of C does not exist, okay, because there's not a value for C for the function. And we also have to have that the limit as x approaches c of this function does exist. And in this case it does. The limit as x approaches c of f of x does exist. because it's the same from both sides. So we have f of c does not exist, the limit does exist for that graph. Another situation, another very similar one with the whole. Let's say that we have that, but it's a piecewise function, and also there's a place in the piecewise function where they have defined that value. So in that case, f of c does exist. F of c does exist, so it doesn't fit this rule. F of c exists. However, that f of c value, that y value there, is not the same y value that the limit produces. So what we would show there is the limit as x approaches c of f of x. It exists, but it is not the same, or it does not equal the function value at c. Either way, the removable discontinuities are wholes, and they can be removed. That might seem like a strange concept, but basically it's removable because we can redefine the function or extend the function, a piecewise function, to fix the problem, to remove the discontinuity. So it's removable because, I'll write this down, we can redefine the function or extend the function is the better term, to basically fix the problem or the hole. We fill the hole. And I'm going to give an example of this. So we would create a piecewise function for this. So let's say our original function was just some stuff over x minus c. Maybe we got to that point by eliminating a binomial eliminate the binomial x minus c by factoring. Anyway, x cannot equal c. We have some kind of function that creates a hole there. So what we would do, we would have that as one part of the function. And then the other function, we would have the y value that we need to fill the hole. And that would be what is valid at x equals c. So basically, this part, what we're doing here is we fill the hole with a point. So it's just temporarily redefining the function so that the discontinuity is removed. Then you're left with just a continuous function. So those are removable. Let's talk about essential or non-removable functions. Non-removable discontinuities. These are ones you can't do anything about. You just have to live with them. So they're called essential. And these are this terminology that you're going to need to be able to use. So we have actually, there's three situations here, two main ones. So I'm going to divide this into two sections here. So the first type, I'll do the graph first. The first type, say, usually it's generated by a piecewise graph. So let's say we have this situation, and this occurs at point C. This is actually called a jump discontinuity. The jump discontinuity, and it occurs when the limit as x approaches c of f of x does not exist. Actually, that applies to all of these. The limit as x approaches c of f of x does not exist at c. And in this particular case, why does that happen? Because the limit as x approaches c from the left does not equal the limit as x approaches c from the right for this function. So I'm just going to shorthand it here. The left-hand limit does not equal the right-hand limit, the jump discontinuity. The next type of discontinuity here that's essential and non-removable occurs when you have a vertical asymptote. So we'll sketch this out. And let's say we have a vertical asymptote here, and perhaps the graph is doing this. So at a vertical asymptote, again, the limit as x approaches c of the function does not exist. Going to positive infinity here, negative infinity there. This is called an infinite discontinuity. So for the essential non-removable discontinuities, we basically have a jump discontinuity or an infinite discontinuity. There is one other time that we would see this kind of non-removable discontinuity when we have oscillating functions. This would be like sine of 1 over x, where it just oscillates back and forth rapidly. That is non-removable too. So that's more of a unique case, but you'll see it. Okay, why are these removable? Excuse me, why are they non-removable or essential? Is because the function cannot be redefined to fix the problem. Just realized I'm off the page. So it can't be redefined to fix the problem. And I think the best example of this is, unlike the hole, where we just had one single point to fill, if you consider this one, in order to bridge this gap here, you would have to fill in a lot of holes. You would have to fill in all of this gap. But then it wouldn't be a function anymore, because it would not pass the vertical line test. You're not allowed to fill a vertical space with a bunch of holes. So that wouldn't work.